Now let's dive into the FFT algorithm. It's a divide and conquer algorithm, so let's start with the base case. The base case is when n equals 1. What are the roots of unity in this case? Well, it's just 1. So we can simply return a evaluated at the point 1. Now we have to partition this vector a into a even and a odd. These correspond to the polynomials a even and a odd. So let a even, the vector a even, be the even terms in the vector a. So a naught, a2, a4 up to an minus 2. And the a odd are the odd terms. So a1, a3 up to an minus 1. The input vector a was a vector of size n. These two vectors, a even and a odd that we just defined, are vectors of size n over 2. Now we have our two recursive steps. We call FFT this same algorithm with the vector a even, and instead of omega, we use omega squared. And we also call FFT with a odd and also omega squared. What do we get back from this call? What we get back is a even at the square of these endpoints, which are these n over 2 points. Omega naught, omega squared, up to omega to the n minus 2. So if omega is the nth root of unity, then we get a even at the n over second roots of unity. And similarly, we get a odd at the n over second roots of unity. Notice that if omega equals omega sub n, then the jth of these points squared, this is the jth point in this sequence, or actually the j plus first. This is omega sub n over 2 to the jth power. So this is the jth, or j plus first, of the n over second roots. Now using these values for a even and a odd, we can get a at the nth roots of unity. Now we use our formula for a of x in terms of a even and a odd. So a evaluated at the point omega to the jth power equals a even evaluated at this point squared plus omega to the j times a odd at this point squared. And similarly, if we look at the point omega to the n over 2 plus j, this is the opposite of omega j. So using the same formula, this requires a even and a odd at exactly the same points. The only difference is we subtract these two terms instead of adding them together. This takes order 1 time for each j, so it takes order n total time. Finally, we have a evaluated at these n points, and that's our output that we return from the algorithm. Now notice this algorithm works for any omega which is an nth root of unity. We only require that omega to the jth power is opposite omega to the n over 2 plus j. That's true for any root of unity except when omega is 1, because then this would be 1 and this would also be 1, so they're not opposites of each other. But for any other root of unity, the jth power is opposite the n over second plus jth power.